Hello. So you've already heard several people talk about this before. So I'm Juliet and also Jesse, though maybe it's going to be a little bit less obvious how what I talk about is related to what Jesse talked about until the end. So I'm going to say some of the same things over again, kind of under the assumption that it might be good to hear them twice. Okay, so we're going to start with the same setup that we've had for a couple of talks now. X is going to be a smooth projective toric variety. S is going to be its total coordinate ring, or Cox ring. This is a graded ring over a non-standard grading, generally. It's graded over the class group of the toric variety. We've assumed smooth, so class and Picard is the same thing. This is just Z to the R for some R. So maybe let me write that. And B is going to be the irrelevant ideal of the toric variety, which is inside S, and it will be monomial. We're going to see some examples of this. I hope to live up to the claim that this is going to be very explicit. We're going to actually use particular irrelevant ideals in a bit. But the reason why this is the setting that we're interested in is because we're going to use the correspondence between sheaves and modules that Juliet talked about yesterday. So one of the nice things about toric varieties that Cox figured out in the 90s is that finitely generated graded S modules correspond to coherent sheaves on X. And so we're going to denote this by sending M to M tilde. This is, if you've seen this construction over projective space, it's a similar idea. You define this by taking localizations over various open sets inside the toric variety. And one thing that we're going to use about in particular is that there are some modules that go to 0. So this is not a one-to-one correspondence. A module will go to 0 if it is supported inside the irrelevant locus. So this irrelevant ideal is describing the points that we remove to construct X. And so if our module only has, its only localizations are non-zero inside the part we've removed, then it just goes to 0 under this correspondence. Another way of saying this that we will use is that it's annihilated by some power, because it's finitely generated, it's annihilated by some power of the irrelevant ideal. Okay, so then we have seen this definition before by Burkash, Urban, and Smith. That a virtual resolution is going to be something that becomes a resolution once we use this correspondence. So it's going to be a complex or I should say virtual resolution for M, is going to be a complex of free modules so that when you take the associated sheaves of term by term, that is a resolution of M tilde. And in particular, because we started with a complex of free modules, this is going to be a resolution of M in terms of direct sums of line bundles. So if you like thinking on the geometric side more, you can just think of virtual resolutions as being resolutions by direct sums of line bundles. But we're going to do commutative algebra, so we're going to want the free modules. OK. So then the question that several people have asked already is, do short virtual resolutions always exist? And by short, we're going to mean length less than or equal to the dimension of the space. And I do want to say a little bit about the naming short here is a little bit misleading because they're always going to be the length equal to the dimension of the space, the way that we're constructing them, basically. So in some sense, we're trading how long they are for knowing that they're less than the dimension of x. Like, for instance, in the classical case, if you start with a module like on projective space, and you truncate it, this is going to make your resolution longer in many cases, but it'll make it shorter in the case where you started with something that was too long, if that makes sense. Like, it's always going to end up at dimension of x. So if you start with something that had a shorter resolution, it's going to get longer, but it's always going to be less than the dimension of x. And we'll see more examples of this in a bit. So short is a little bit of a weird thing to say, but this is what we tend to call them. And I also want to say what I mean by length in case you're not used to working with free resolution so much. So the convention here is that we are counting the number of maps. So we want our last free module to be at the dimension of x. It could vanish before this, but this is the last possible spot. So that's dimension of x many maps and not dimension of x many modules. Questions so far? OK. And we know that the answer to this question is yes. On many counts. Many people have proved this. We've heard a lot of names before, Hanlon, Hicks, and Lazarev, Jesse, and David Favero, Anderson, Brown, Ehrman. In special cases were known before that. However, most of these constructions are not very easy to compute. So they generally use either derived functors or mirror functors, both of which are not known for their ease of computability. At least for derived functors, like if you just want to compute an x module or something, you can do that. But we're going to want the actual complex that comes out in the not just the homology. And if you want the actual complex, you've got to start computing injective resolutions and stuff like that. And so this is maybe a little bit doable, and I guess this might be doable for some people, but we're going to try to construct these resolutions in a way. It's not doable for me. We're going to try to construct these resolutions in a way that I can explain to you in 5 minutes how to do it, OK? So that's the goal. Explicitly describe. And I'm going to stick, people can't see over here, can you? OK. Let's try to stick.
That corner is the problem. That corner's good.
Well, that corner is good for you. I think these people may beg to disagree. But so I'm going to stick to a particular proof of this. So there's several different constructions floating around of these short virtual resolutions. Many of them are very related, but I'm just going to stick to one for now, and I'm going to call the functor phi. So there's some functor that's going to take a module and give a short virtual resolution, and I'm going to use the one from the Hanlon, Hicks, and Lazarev construction. OK, so let me say a little bit. Well, actually, first, let me motivate this slightly. So why might we think that these resolutions even are describable in a nice way? And Juliet sort of gave the answer before, that there are some cases where we know how to describe them. So somehow the motivation here for trying to figure out the answer to this question, at least for me, was coming from a theorem that I proved along with Juliet and that and Mahrad Seyrafi that she talked about yesterday, that if X is a product of projective spaces, and for ease of stating this, I'm just going to assume that it's a particular product of projective spaces. You can do this generally, but the notation just gets more annoying. So let's say that we have X equals P1 cross P2, which was the example that Juliet did. In this case, the total coordinate ring, you have 2 variables for P1 and 3 variables for P2. And the irrelevant ideal is the intersection of the ideal generated by the x's with the ideal generated by the y's. So this is representing the fact that if you want to construct P1 cross P2, your points are going to have 5 coordinates, or sorry, 5 coordinates, and you need that that at least one of these 2 is non-zero, and that at least one of these 3 is non-zero. So in this setting, we were able to show that under some regularity condition that's not going to be super relevant here, but if our module is regular at some bi-degree CD, so this is graded over Z2, where the P1 has one grading and the P2 has the other grading, then the truncation of M at this bi-degree, so this is going to be component-wise. So we want to take all the elements in M that have degree greater component-wise than CD. Sorry, this part's going to be an if and only if. So this was that this module has this word that we haven't defined, a quasi-linear minimal free resolution. But then the part that we care about here is that this particular resolution is always short. And this short resolution is actually an example of the type of a virtual resolution for the not very intense reason that if you take the module and you mod by this truncation, this thing vanishes in like high degrees somehow, like in high degrees in both coordinates. And so in particular, if you multiply it by some high power of b, the elements of b have degree 1, 1, and so you're eventually gonna get 0 if you do this. Is this believable? So in particular, these 2 modules define the same sheaf, because I said that if you are annihilated by b, then you define the 0 sheaf, so the difference between these 2 things is the 0 sheaf. So this resolution is an example of a short virtual resolution. And so this was kind of motivation for thinking that maybe we can get short virtual resolutions that are easy to describe. Like this is a very easy module to construct. You can get a computer to do it. The code runs very fast. And so this was kind of why, at least I thought that maybe we could get a nice description of virtual resolutions for other torque varieties. Okay. So this functor here that I was talking about that comes from this proof, I said it was a type of derived functor. I want to say a tiny bit about how they define it. This uses some machinery. It's sort of a well-known construction in derived algebraic geometry called a Fourier-Mukai transform. So this is a type of derived functor that's well studied in derived algebraic geometry. It's like a class of functors, and this is going to be one of them. So what we're going to do is we're going to take our torque variety and take the product of it with itself. There's two projections. And sort of the genius of this plan is that if you want to get short virtual resolutions for all sheaves on X, it's enough to resolve one sheaf on X cross X, namely the sheaf of the diagonal. So we're going to have some K here. I can figure out how to write a script K that resolves a diagonal. So the diagonal meaning like X comma X, so the structure sheaf of that. Inside here. And constructing this thing is the hard part of several of the proofs of the existence of short virtual resolutions. So if you can get a resolution of the diagonal, then getting the rest of them is just a matter of applying this type of functor. So what you do, what I've been calling phi here, so I'm going to have phi take a module, just so because that's what I'm doing. So if you start with a module, really maybe it should take a sheaf, but what we're going to do is we're going to pull that module back to the product. So we're going to take its sheaf and then pull that back to the product. Then we're going to tensor that with this resolution of the diagonal. Because the projection is nice and this is a locally free, I guess I didn't say that. This is going to have to also be a resolution in terms of line bundles. Because the projection is nice and this is nice, both of these are technically derived functors, but we don't have to do anything. We can just pretend that they're not and just do the normal functors. But then we're going to push it forward to the other factor, and now we legitimately need to use the derived functor here. So this is the hard part somehow. And this gives some complex of sheaves. And that's going to be our, so this thing is going to be the sheafification of our short virtual resolutions. This is going to be F tilde for our M. And the notable observation here is that for sufficiently high D, and by this I mean sufficiently ample D. So pick some ample divisor and then take like a high enough power of that. Phi of M twisted by D will have the same length as K. I guess yeah. So for low D, it might even not be a resolution. It might just be a complex that goes on both sides. Like it might have a negative term. But if you pick high enough D, you'll get an actual virtual resolution. And if you get K to be the right length, you can get this one to be the right length too. Yes? So I'm twisting so that it's a legitimate resolution and not a monad, for instance. Like so that it doesn't, we want to have like F0, F1, and so on.
So the output of Fn is also basically
Yeah, so the output exists regardless, but like we don't want an F negative one, and we also want it to be the right length. But you can get an output regardless.
You want this to be a resolution of the value started with M. Some of this is formalism that gets you enough to do that.
Yeah, and you can kind of understand what the formalism might be without knowing too much. Like, if you just think about, forget any of the derived stuff, and think that you're starting with some like subvariety here, and you pull it back, and you restrict to the diagonal, and then you push it forward, you get the same thing back, right? That's kind of the intuition behind why this yeah. So maybe I should say that here too. So this will be a virtual resolution of M, and we'll have the same length. Okay, thank you. But somehow the fact that it gives a virtual resolution of M just comes straight out of the machinery. Like the new part is that you can get it to be short. Other questions? Yeah. Oh yeah, thank you. But you can get that, you can just twist it back down. Yeah. No, generally you have to twist ample, yeah. Okay. Oh, yeah.
Is there something you know about this projection key so that RP will start to like increase the length of?
So that's what one of the things that the twist is doing. Yeah.
Okay, so derived push forward of a complex locally free objects. Twisted sufficiently high.
Like, why is it still locally free?
Yeah, I guess.
So that comes from the projection formula. Like after we tensor with M, it's not locally free anymore upstairs, but then the projection formula says that it will be downstairs. Yeah. Okay, so my work here has been in actually describing what comes out of this in the specific case of putting the ring into the functor. So this might seem a little bit silly because if I asked you to give me a short virtual resolution of S, you could probably do that. You just give me S back, right? It has a very nice short virtual resolution. And this is the sense in which we're trading short for like exactly the dimension length. So we're going to get a longer thing out of this. But the idea is that we can start with these ones and then build the other modules out of this. And I can just describe how you get this in a particular example. So this is like the standard example that Jessie had, and I'm going to get similar pictures to her for reasons that might not be totally clear. So I'm going to start with the Hertzberg surface 2. This is a particular P1 bundle over P1. Here, the coordinate ring has 4 variables. The irrelevant ideal looks like that. So you can kind of see that this is like a twisted version of P1 cross P1. Like it has the same irrelevant ideal. And it's Z2 graded, so this is non-standard graded. The degree of X and the degree of Z are going to be 1, 0. The degree of W is 0, 1. And the degree of Y is -2, 1. So this is the 2. And that's like, this is sort of like the divisor that's telling you how the bundle works. Okay, and so I'm going to show you how to construct a particular Fourier-Mukai transform, hopefully in a understandable way. Like I think this construction is pretty easily computable, and I have code to compute it as well. So I'm going to do, I guess I should put the actual D. I'm going to do phi of S twisted by 1, 1. Okay, so what we're going to do is we're going to take, let me just make sure I get my, we're going to start with the monomials of degree 1, 1 in this ring. So this is a non-standard graded ring, so it's not immediately obvious which monomials have degree 1, 1. But if you're familiar with toric varieties, those monomials fit into a polytope. So I'm going to draw them in a suggestive shape. Okay, so these are all of them, and they fit into a polytope like this. You might be able to see, even if you're not familiar with this, how you might arrange them like this. Oh, I guess I should give you the fan of this toric variety. So if you think about the fan of this toric variety, it looks like this. And you might be able to see that, like, to go this way and this way, we're multiplying by monomials coming from the columns of the ray matrix, something like that. Okay, but what I'm going to do is I'm going to start with this polytope. It's a trapezoid. And the walls of this trapezoid are normal to the vectors in this fan, and that's not a coincidence. And so what I'm going to do is I'm going to translate all of those hyperplanes into my polytope wherever they hit lattice points. So like this one, this vertical one, I'm also going to put one here, and I'm going to put one here, and then this one is not going to be relevant. For this hyperplane, I'm going to, I already have all of them because there's no other horizontal lines between lattice points. And then this diagonal one, there's going to be a few more. So there's one that goes here, and there's one that goes here. Does it make sense what I did? Okay, so we get 3 new points here. And we're going to label these as if they were in this picture. Like, okay, to go from here to here, we added 2 z's and got rid of a w. So to get here, we're going to add a z and get rid of half a w. And then I'm going to take the ceilings. So this is going to be y. Oh, sorry. We added a y and 2 z's and got rid of a w. So we're going to add the whole y, add only 1 z, and keep the w. So this is like the ceiling of what it would be if I did the fractional version. Does that? Okay, and then label these other ones as well. And then the output that we want is going to be a complex that you get from this using the type of thing that Jesse just described. So we're going to get 3 terms like this that come from the vertices, the edges, and the faces of this little picture here. And that's what comes out for this. And again, this is not a very useful short virtual resolution, but you can build the resolutions of other modules from this one. And in particular, you can use this to see that the output of phi is not always a resolution. So far, all of our virtual resolutions have just been like honest resolutions of different modules. But you can actually use this to construct a module so that, so a corollary of this is that phi of m is not always exact. And that was a surprise to me and something I was excited to find a virtual resolution that was legitimately virtual and not just a resolution of a different module. And I will stop there.